Hello. So in this video, we're going to look at Haberman's section 3.5. So in the last section, kind of the goal was to make sense of differentiating Fourier series, right? So you have a function, you have its Fourier series, and then what you want to do is take the derivative of each side, say the function and its Fourier series. And then the question is, when is kind of the derivative of that Fourier series the Fourier series for the derivative of the function? And at least, yeah, if the Fourier series is continuous, then kind of they match up, all is well and good. If the Fourier series is not continuous, you can kind of construct a formula that tells you kind of how the two relate, but the nice and the easy to work with setting is when the Fourier series is continuous. So in this section, what we're going to do is we're going to kind of go the reverse direction. And so our goal here is to make sense of when the Fourier series of an integral is the integral of the Fourier series, right? So you have a function, you have a Fourier series, you integrate both sides. The question is, right, is the integrated series the Fourier series for the integrated function? And kind of the answer we'll see is that, well, almost. Okay. And so it turns out that the setting is nicer than kind of differentiation. And the integrated series will almost be the Fourier series of the integrated function. It's just you're also going to have this polynomial that shows up. So let's see how that works. Okay, so our setup, here's our given function, f of x, and kind of the integrated sort of kind of an indefinite integral, but we're specifying a lower bound and we're keeping the upper bound, you know, whatever. So capital F of x will be the integral of little f of x. And what we're going to do is we're going to just take the Fourier series for f of x, right? And so kind of looking at the integral, implicitly what we're doing is we're saying kind of on this interval negative L to L, here's this series. Okay. And so then the question that we'll start with is, well, what is a Fourier series of this function, which we write as this integral? So in a sense, we're asking what is a Fourier series of the integral of this function? Okay, and then the question is, can we relate it back to this? The Fourier series of the function. And so our approach will essentially just be, well, let's compute it. Let's go ahead, plug and chug, see what the coefficients are, and then try to relate them to kind of the integrated series. Okay, so the first observation is that, well, kind of the integral of our function from negative L to L, that's going to be 2L times A0. Okay, why is that? Well, this is essentially the definition of A0. Right, A0 is 1 over 2L times that integral, so the integral is that. So what does this tell us? Well, what is f of negative L? Right, again, where f of x, this was integral from negative L to x of f of x dx. Well, if you plug in negative L here, right, you're integrating from negative L to negative L. So you're not really integrating over kind of any region that actually has an area to it. So f of negative L, that's just going to be equal to 0, right? What is the integral under a point? Well, again, area underneath is 0, so just get 0. Okay. But the thing is, that is not equal to 2L times A0, which is exactly equal to f of L, which, plugging in the definitions, this is integral from minus L to L of f of x dx. Okay. So kind of this, the integral is not necessarily going to be continuous between, or the periodic extension of f of x will not necessarily be continuous, right? Because the value of capital F of x at the two endpoints is what we just saw, possibly different. Okay. So that's already something kind of we need to keep in mind. Right, so the periodic extension, as I just said, periodic extension of f of x, and hence the Fourier series, they will not be continuous. Okay. This turns out, though, it's not too much of an issue, because what we can do is we can modify this function f to get something that will be continuous, and then its Fourier series will be kind of nicely behaved, and then we can get some traction. Okay. So what we're going to do is we're going to define a new function g of x in this way. Well, we're going to take the integrated function f, and then we're going to subtract from it a0 times this polynomial x plus l. Okay. And so, yeah, you can make an interpretation of this term right here. So this a0x plus l, in a sense, this is a line segment that connects kind of the value f of minus l to the value f of l. So it's just kind of that straight line segment and whatever. You can also think of it as, well, it's just a function that works to kind of make the endpoints equal. We're good to go. Okay, so if we define this new function g of x, right, well, what are some properties it has? If we plug in negative L, or just plugging it in, here's what we get. Okay. This we saw before, right? This term right here is the integral from negative L to negative L, which is 0. This stuff right here, this is also 0. So g of negative L is 0 minus 0, which is just 0. Okay. On the other hand, what is g of L? Well, plugging it in, we're going to get f of L minus a0 times L plus L. Okay. This is the integral from negative L to L of f of x dx, which we saw was 2a0L. And we see here, this is a0 times 2L. Okay. So we get 2a0L minus 2a0L, which we cancel. So g of L is also equal to 0. Cool. So, right, what we get here is, well, the kind of this function g, the value at its endpoints are going to be equal to one another, and they're both going to be 0. But what else do we have to work with? So this thing right here, this is a polynomial. Polynomials are kind of continuous functions. And kind of the last fact that we need to deal with is, well, f of x, this integral, this is also continuous. Okay, and this is a general fact about integration. The integral of a function, kind of, right, when you leave one of the endpoints for your integral open, kind of the resulting integral is continuous with respect to that argument. Okay, so we can summarize. So g of minus L is equal to g of L. F of x is continuous. So g of x is continuous. Okay. So g of x is continuous. And so kind of the theorem that we had before was, well, right, if g of x is continuous, then the Fourier series defined everywhere on the real line, that will also be continuous. The fact that the Fourier series is continuous also relies on the fact that the endpoints agree. Cool. Okay, so we know that the Fourier series of this g of x, which is the integral minus this polynomial, that's going to be well behaved. So let's go ahead and compute some of these coefficients. Okay. What we're going to do is we're going to call g of x, we're going to name the pieces of the Fourier series kind of with tildes. Okay. And so our goal will be, well, how do these kind of a sub 0 tilde, a sub n tilde, and b sub n tilde, how do each of these coefficients relate to the coefficients of f of x, right, the non-integrated version, which are just kind of a0, a sub n, b sub n. Okay. So our question is, how do these coefficients relate? The way that we're going to answer that question is just integrate, compute these things. Okay. So what is a sub n tilde? Well, a sub n tilde is, right, the integral, so 1 over half the length of the interval, integrate over the interval of the function we care about, right? So in here, this is g of x, times kind of the function that it's a coefficient for, which in this case is cosine of n pi l over x. Okay. So what is this? Well, what we're going to do is we're going to distribute this cosine of x to f of x. We're going to distribute to minus a0x and then minus a0l. So the first one is that. Second one is that. Right, so here this was this distributed to the minus a0x. And then finally we end up with cosine distributed to minus a0l. Okay. Okay, so now the question is, well, what are these integrals? So two of them we can already kind of ignore because they're 0. So here, the observation is, well, cosine is an even function, and there should be an x in here. Cosine is an even function, x is an odd function. So if you integrate these over the entire kind of interval from negative L to L, you're actually going to get 0. Okay. That's the quick description. If you go through the process, right, integration by parts, compute things, it's also going to get 0, but you're going to get 0. But okay, so this thing is 0. This thing down here will also be 0, and kind of there are two ways you can see this. Well, one of them is you're integrating a constant times cosine of n pi over Lx over its entire kind of period. Okay. So wherever cosine is positive, we'll cancel with wherever it's negative. So the integral will be 0. Another way you can think of this is, well, right, cosine of 0 is technically one of the functions, kind of one of the basis functions for cosine. Right, in our integral identities, they say, well, right, cosine of n pi over Lx times cosine of m pi over Lx. The integral of that is going to be 0 whenever n and m are different. And so in a sense here, we're computing the product of cosine of 0 times cosine of, right, n, which is non-zero, pi over Lx, and those should cancel. Okay, but the point is that this is 0 and this is 0. So what do we end up with? Well, we end up with just the first term, right? 1 over L, integral from negative L to L of capital f of x cosine of whatever. And so keep in mind that this function capital f of x, this is the integral, I can write it again, right? Again, capital f of x, this was the integral from negative L to x, f of x dx. Okay, so now we're integrating the integral of something times something else. And we're going to evaluate that. Okay. So it would be nice if we could relate this to little f. Okay. And in general, we have a tool for, or a technique for, right, integrating or taking the derivative of functions, right, in the integral of a product. And that's integration by parts. Okay. So we're going to apply integration by parts to this in a way where we take the derivative of capital F of x so that we see little f of x show up. Okay. So what are our pieces? U is going to be capital F of x. Du is going to be little f of x dx. dv is going to be cosine of n pi over Lx dx. The integral of cosine is sine. Okay, don't have a positive or we don't have a negative sign in front. Otherwise, we need this L over n pi in front. You can check this. If you take the derivative of this, this constant in here is going to pop out, going to cancel with that. We're going to be left with cosine of n pi over Lx. Okay. Anyways, these are the parts for integration by parts. Okay. So what happens to this integral? Let's see. So we're going to keep this 1 over L in front. Okay. So what is integration by parts? Maybe I can write it up here. So the integral of u dv is equal to, say, from a to b. This is u times v evaluated from a to b minus the integral from a to b of v du. Okay, so plugging things in, we have u times v evaluated between, so u times v evaluated between negative L and L, minus the integral of v du. Okay. Okay. And so now what we can do is we can evaluate this. Well, here we're plugging in L and negative L, right? They're going to go in here. We're going to be left with sine of n pi for an integer n. So these terms are all going to be 0. Otherwise, you're going to notice that, right, when this 1 over L comes in, okay, and then bring this constant L over n pi out, what we're going to end up with is L over n pi times 1 over L, the integral of f of x sine of n pi over x, or n pi, it should be n pi over L times x. Okay. But that piece is exactly, right, capital B sub n, which was the Fourier coefficient of f of x in terms of the signs. Okay. And so that's this thing right here, where, right, why? Well, B sub n, we define this to be 1 over L integral from negative L to L, f of x sine of n pi over Lx dx. Way back up when we said that the Fourier series of f is this, right? So that's what this B sub n is. Okay. Cool. So, right, this was a computation for a sub n tilde, the coefficients for the cosine pieces of g of x. Okay. So a sub n tilde is going to be minus L over n pi b sub n. Likewise, b sub n tilde, same exact process, integration by parts, things fall out, whatever. You're going to get L over n pi times a sub n. Okay. Okay, so this is the case for, right, n greater than or equal to 1. I should clarify up here, this computation here was for n greater than or equal to 1. Okay, what about n equals 0? Well, note that, so g of L is equal to 0, right, which is what we computed above. So what does this give us? Well, so g of L is 0. Fourier series of g converges to the function g itself, at least on the interval negative L to L. Okay. So what we're going to do is we're going to plug in L to the Fourier series of g, where we've computed almost all the coefficients. Okay. And because g of L is equal to g of minus L, right? The value of the series at L is just going to be g of L. right? That's this Fourier series converges to G. Okay, so plug it in. 0 is equal to G of L. What is G of L? Well, if we go back here and we plug in L right there, okay, we're going to get an L right there and an L right there. These are all going to go to 0 because we have a sine of n pi. Otherwise, you could almost see what we're end up with. So this, zoom in. Okay, so that's what we get almost if we plug in L. This isn't quite correct because this should be 0. This should be an L. This should be an L. Okay. Simplify a little bit. Let's see. So these sine of n pi's, these are going to go to 0. Okay. So all we're going to see are these a sub n tildes times cosine of n pi. Okay, so we have that cosine of n pi there. But what was a sub n tilde? Right? That was exactly minus L over n pi b sub n. Okay, so we're going to plug this in wherever we see an a sub tilde. So this becomes minus L over n pi b sub n. Pull out the minus sign. This is what we end up with. Oh, and look, we have a way for computing a sub 0 tilde. So moving things around, we've computed what a sub 0 tilde is. Okay, it's just a series, right? Sum of n equals 1 up to infinity of L over n pi times b sub n, right? The sign coefficients in the Fourier series for little f of x times these other terms cosine of n pi. And we're not going to worry about simplifying cosine of n pi to positive, -1, etc. We're just going to leave it like this. Okay. So, right, Fourier series for g of x, right, again, because g of x is continuous and its endpoints agree, g of x is going to be equal to its Fourier series. This is what we named all the pieces. Okay. So let's just start plugging things in and seeing what we get. So the first thing we're going to plug in, right, g of x here, remember we said g of x, this was capital F of x minus a0 x plus L. Okay. So we're going to plug in kind of those two pieces that we used in defining G. What else do we have? Well, the a sub 0 tilde, we're going to plug in for the series right here. A sub n tilde, we can plug in for those in terms of the Fourier series for f. And finally, the b sub n tilde, we can plug in for those to get this. So the Fourier series that we were really interested in was for this capital F of x. Right, so let's solve for this capital F of x. Right, what does solving entail? Well, we needed to move this polynomial piece to the other side. So it's right there. Okay. Otherwise, what we're going to do is we're going to collect terms in a way, right? So up here, right, we had these b sub n with a bunch of stuff going around. And we also had these b sub n over here with a bunch of stuff associated to them. Okay. Keep in mind that nothing here had an x dependence on it, but that's okay. What we're going to do is we're just going to collect these b sub n together. And so we end up with this. Likewise, there's not much to do with the a sub n, but okay. So this is f of x. This isn't quite a Fourier series, in part because, right, this polynomial right here isn't, what is it? Right, it's not a trigonometric function, okay? But, right, in a sense, the rest of the stuff is, okay? Right, this bit right here is going to get us our constant. Otherwise, you have the cosine piece and you have the sine pieces. Okay. And so this is one way to kind of look at the series expansion for f, which is going to kind of be the most convenient in a second. We just integrate the series and see what happens. But another way to kind of think of this is, right, well, we almost have a Fourier series here, right? If you ignore this polynomial piece, and if you ignore or explicitly bring in or whatever this other constant here, right? In a sense, we have a Fourier series plus a polynomial, and that's what we get for this integrated function. Okay, so we're going to write it in that way. So collect a sub 0 x as well as kind of this constant piece there. Okay. This is going to be kind of a polynomial. I mean, yeah, it is a polynomial. Likewise, we're going to kind of collect this a sub 0 L. And then we're just going to have kind of the cosine terms and the sine terms. So at least written in this way, right, maybe a little more explicitly, this bit or some combination of those, that's going to be the polynomial piece, right? So this is going to be, right, actually, let me write it this way. So this right here, this is roughly the polynomial. This right here, this is roughly the Fourier series or a Fourier series. Okay, so up to a polynomial, right? The integral or the how is this? It's almost a Fourier series up to a polynomial. Okay. But this is what we get just by saying, here's our function. It's the integrated little f of x, right? Capital F of x. Let's compute the coefficients directly. This is what we got, okay, up to a polynomial. So now the question is, well, how does this compare if we had just taken the Fourier series of, right, little f of x and integrated all of those terms? Okay, well, let's take a look, right? So is this the integral of, right, all this stuff here? And by that we mean, well, if we integrate from negative L to x, integrate from negative L to x dx over here, integral negative L to x dx over there, do those agree? Well, let's integrate all of this stuff, right? So we're looking at the integral of the series, again, assuming that the integral kind of distributes over these infinite summations, which we're not going to have a problem with. We're going to say it's valid. So what happens over here? Well, integral of a0 between x and negative L. That's going to be that term. Okay. What about the next term? Well, here, a sub n is a constant, so it's not affected by the integral. Integral of cosine of n pi over Lx. Cosine goes up to positive sine once we integrate that. Otherwise, we need to bring kind of this out and take 1 over it. So the integral of these pieces is going to be a sub n times L over n pi sine of n pi over L times x. Okay. And keep in mind that here we have a definite integral, so we also have bounds we need to evaluate kind of these integrals between. Likewise, we can do the same thing with these sine pieces. Okay, the integral of sine, this was minus cosine. Otherwise, keeping track of the coefficient or that constant inside, this is what we end up with. Again, evaluating bounds. Okay. Cool. So what does this give us? Well, nothing to do with the a sub 0 piece. Here, we're plugging in negative L there. So we're dealing with sine of n pi, which is going to be 0. Okay. Otherwise, we're plugging in x, and that's just what it is. So evaluating each of these terms at the bounds, we're going to end up with just a sub n, L over n pi, sine of n pi over Lx. Okay. Okay, what else? Well, here, okay, evaluating here, we're going to get kind of b sub n minus L over n pi. Actually, let me write this out. So this right here, this is going to be b sub n, all right, minus L over n pi times cosine of n pi over Lx minus L over n pi cosine n pi over L times minus L. Okay. So these minus signs, they're going to cancel. So we just get a plus here. Cosine of minus whatever is cosine of whatever. So this whole thing is going to simplify to cosine of n pi. Okay. So we're going to get minus, right, all of this plus cosine of n pi. So I haven't yet simplified, but so if we go through and simplify it, it's exactly what I said. Yeah, cool. So what we've seen is if we just go ahead and integrate the Fourier series, right? Well, we're going to get this polynomial piece plus a Fourier series. Almost. I mean, that, but whatever. But what we've seen is, well, right, again, if we integrate the Fourier series, this is what we end up with, which exactly agrees with what we computed up here, right? Where we took this function g of x, which was this minus that, right? So subtract off that polynomial part, you should end up with the Fourier series, add back that polynomial part, we're good to go, okay? So the takeaway is that integrating Fourier series, that's all well and good. No issues there, okay? The only thing to keep in mind is that technically, right, the integral of a Fourier series is not a Fourier series because you have this polynomial in front. But if you just want to evaluate, if you want to look for identities, if you want to do whatever, that's no problem. We have equality of these two things, okay? So take away from these two sections, integration, great, works well, does what we want, no issues. Differentiation is a little, you have to be a little more careful with, but as long as your function is continuous and its Fourier series is continuous, or function is continuous and the value at the endpoints agree, then you can differentiate the Fourier series, no problem.